welcome in today's video. Today we are going again through another force method example. We have a new shape frame for which we have to solve by using the force method the reactions at point A and at point B. We have given that A and point B are assumed to be pins and joints C and D are rigidly connected, which is basically a fixed connection. The flexural rigidity of the members is assumed to be constant everywhere for all the members, and we have the distributed load Q acting on member AC. We have the given dimensions A and B. We are going to solve the problem parametrically in order for us as engineers to use the results in the end if something changes. For example, if this length is changed or the value of distributed load is changed. So without any further ado, let's start to solve this by using the force method. And as we have done on the other cases, the first thing to be done is to determine the degree of indeterminacy for the structure. We have four reactions which are coming from support A and support B. We have two reactions here and we have two reactions here. In total, we have four. We have three equilibrium equations. And if we do the difference, we are going to get that the degree of indeterminacy for this structure is going to be 1. Let's apply the force method, and in order for me to solve this exercise, I decided to release one of the joints, which for this case is C, and make it an internal hinge. And after I do this, the structure is becoming statically determinate, and it's easy to solve. And also we have to add case 1, for which we are going to apply a virtual bending moment at joint C, which we released. So let's start to solve for case 0. As now the structure is becoming statically determinate, it is easy to determine the reactions for this case. So I decided to take sum of bending moments at point A to determine the value of support reaction B0, which is going to be as shown here. Next, we can take sum of forces on y directions in order for us to determine the value of support reaction A0, as shown here. And now if we analyze member AC separately, and if we take the sum of bending moments at the hinge, as we already know that since we induced an hinge, the bending moment there is going to be 0. And if we take that sum of bending moments at the hinge is going to be 0, we are able to find the value of support reaction A01 as shown here. Next, for the whole frame, we can take sum of forces on X, and then we can determine the value of support reactions B01 as shown here. In order for us to utilize the force method, the next step to be done is to determine the bending moment functions on the structure where we have discontinuities. And let's start by doing that. So I started from the right side, I think. Yes, B we have here. So I took this section cut from this side and I determined the bending moment function as shown here. Next, I decided to take the cut section from this part and define the bending moment function for these boundary conditions. And last but not least, we have the other discontinuity. I decided to take the cut sections from this side and define the bending moment functions for this one. Next, let's continue to solve for case 0, for which we applied the virtual bending moment at the node which we released. And if we analyze member AC separately and taking the sum of bend moments at the hinge equal to 0, we are able to define the value of support reaction A10, which is as follows here. Next, we can take sum of forces on X, and then we can determine the value of the other support reactions B10, which is going to be as shown here. Next, if we take sum of bending moment at hinge C, we can determine the value of B1 as shown here. And last but not least, if we take sum of forces on y equal to 0, we are able to find the value of support reaction A1, which is going to be 0. After that, as on the previous case 0, we have to find the bending moment functions where do we have discontinuities on the structure. And I decided to take the cut section from this side and determine the bending moment function for these boundaries as shown here. Same thing is done for the other discontinuity. I took this cut section from this distant x and determined the bending moment function. And last but not least, we have the other boundary for which I decided to make a cut section here and define the bending moment function. In the end, we have a summary of results. We have the bending moment for each case, case 0 and case 1, and their respective boundaries according to what we selected. So next, let's apply the force method, and if we apply the compatibility, we are going to get the following equations, for which in order for us to solve, we have to find these two unknowns. So let's start to calculate the first unknown by taking the integrals, and as we already have the table of results here, we can just input them immediately, and then we are going to get that the first unknown is going to have the following value here. Next, let's continue to calculate the other unknown, and we take the integral again, and we define its value parametrically. And in order for us to find the unknown which we were looking for, which is basically the bending moment at joint C for which we released it and solved it by using the force method, we just do this division, and then we are going to get the value of bending moment at point C is going to be this one here. And this is a parametric value, of course. If we want to find the other support reaction, we can apply the force method, as we already now find the redundant which we were looking for. And basically we just apply the force method to get these following values for the support reactions AX, for support reaction AY, BX, and BY. To make sure that our hand calculations were correct, we just assume some values. For the distributed load on member SC, I assume 5 kN is acting on it. I assumed A is 5 meters and B is 5 meters, and I get the following results for these support reactions based on these loads. Of course, if we need to draw the bending moment if needed, we can do that still by applying the force method. We have the bending moment functions coming from case 0 and case 1, and now we just apply the force method in order for us to find the bending moment functions, which is going to look like this for the first part, x1, which is going to be this member, x2 this member here, and x3 this member here. And if we draw the bending moment diagram, it's going to look something like this based on these values. On the next video, I will model this frame using Autodesk Robot software, and we are going to compare the results which we got by hand calculations with the result which we got from the Finite Elements software. So thank you very much for your time. I really hope you enjoyed today's video. If there is any questions, please leave them down in the comment section below. And do not forget to like, share, and subscribe. See you on the next video.